All right, welcome everyone to the last section we're going to cover here in Chapter 2. This is Section 3, Logarithmic Functions and Models. And so yeah, usually if you've experienced logarithms before, I find that most students do not like logarithms. And that's why I labeled them the deadliest of all functions. And they do have a lot of strange rules and properties that are actually really cool functions, and they're really useful for modeling real-world situations. So luckily in this course, we're not going to be so interested in a lot of these properties and cool things that they actually do. We're just going to be interested into logarithmic functions. So that's what we're going to be focusing on here. And then of course, how can we apply these things to real world situations? So let's do a little bit of a reminder here. We have a definition, the base b logarithm of x, which we denote log, and then in a little subscript we have a b of x. So log base b of x. This is the power to which we need to raise b in order to get x. So let's write this down. This is equivalent to saying log base b of x is equal to, and I'm going to use another variable. I'm going to use y here, I guess. This means I need to raise b to the power of y in order to get x. Okay. That means that pretty much every single exponential statement like this has an equivalent logarithmic statement, right? This is a definition. This is an equivalency. They can be traded in and exchanged. So for instance, if I did something like 2 cubed equals 8, this is an exponential type of statement, this would be equivalent to the logarithmic statement of log, my base here, my base of my exponent, this is 2, right? This is my b here, so log base 2 of x. That's 8. So this is saying, which power do I need to raise 2 to in order to get 8? Well, I need to raise it to the third power, right? So again, a lot of exponential statements, pretty much all exponential statements, have an equivalent logarithmic statement. So, let's move on here. As I've noted, right, mathematicians do play favorites. We have a couple of favorite logarithms out there, and they get special abbreviations. So the first one is lnx. This is pronounced the natural log of x. And this is the log with a very special base. It's the e base. So it's log base e of x. So again, this e thing, this is the natural exponential. And so it gets a special name and everything, e, right? But the claim is that it's just a number. So let me pull out our calculator here. And we can actually see these special names of logarithms here. We have log, L-O-G, and we have ln. And that's the one that we just did, the natural log. And you can see right above them we have e to the x and 10 to the x. So if I do e to the x, and I just want to know what e is, so I'm going to do e to the first power here. E to the first power is 2.718 and change. Right? So this is just a number. And you should think of it. It is just a number. It's somewhere between 2 and 3, a little bit closer to 3, but it is just a number. Okay. So that's what the first kind of our favorite logarithm is. And the claim is this natural logarithm applies to a lot of real-world situations. We like natural logs. Okay. And let me maybe just remind ourselves. So this is going to be 2.71828 ... That's what e is equal to. And it goes on forever. It's kind of like pi. Yeah, it goes on forever. It doesn't repeat itself, anything like that. All right, and the other log that we like is just log of x here. And this is shorthand for log base 10 of x. And you know how humans like 10, you know, because the number of fingers and all that sort of stuff. So that's why we like log base 10. And we've made a lot of models and stuff like this, you know, for instance, sound, that really relates well with base 10. Okay, so then finally, everyone's favorite property shows how logarithms can be, you know, all bases can actually be related. Really, we end up using it a lot, though, to evaluate these things in our calculators. So if you have a log of any old base, right? So again, especially in my calculator, I know that there's new fancier calculators out there. Oops, I guess I want this one here. There we go. I know there are new fancier calculators out there and everything, but my calculator only has log, that's log base 10, and the natural log, right? And so how do I do, for instance, like up here I had log base 2 of 8. How could I punch that into my calculator and see that that's actually equal to 3? And the way that we do this is with the change of base formula. This says that log base b of a could be equal to the natural log of a over the natural log of b. And in fact, you can really do this with any base, any other base that you'd like. So it turns out also log base 10 of a divided by log base 10 of b. Right? So for instance, let's do a quick example. Compute log base 4 of 6. Right? So the first thing, I want to think about maybe what are reasonable answers. What, if I get this as an answer, am I happy with? So I'm going to go ahead and first of all just call this equal to y really quick. And I'm going to transform this into an equivalent exponential form. So this is going to be 4 to the y, right? What power I'd have to raise 4 to in order to get 6. And so I want to think about this, right? Powers that I raise 4 to in order to get 6. Well, if I raise 4 to the first power, that'd be too small, right? 4 to the first power is equal to 4. That's smaller than 6. If I do 4 to the second power, that's going to be equal to 16. That's going to be greater than 6, right? So I think that whatever log base 4 of 6 is, it should be somewhere between 1 and 2. Because 1 was too small, and if I raise 4 to the second power, it's too big. Okay, now that we have an idea, what is a reasonable answer, let's go ahead and throw this into our calculator and see what it actually is. So I'm going to pull up my calculator, and I'm going to do the natural log of 6 divided by the natural log of 4. That's using my change of base formula. Again, I don't have a log base 4 button in my calculator, so I need to use the change of base formula. So, okay, enter 1.29 and change. Okay, so this thing actually is 1.29 and change, right? Okay, but let's use the other one, right? So I use natural log here, and I claim that you can use really log of any base. So I'm going to do now log base 10 of 6 divided by log base 10 of 4. The exact same answer. So you can see you can really use any base that you want here. This is one of these mysterious properties of logarithms. Actually, it's not that mysterious. It is a theorem. We can actually prove this thing. But yes, like I said, logarithms had a lot of properties. This is the only one that we're really going to talk about in this class because we need it to evaluate some of these things. Okay, now let's see kind of a more straightforward problem, algebraic type of problem that you may have seen in a previous algebra course. Use logarithms to solve 3 to some power equals 10, right? And that power is 2x plus 1. Okay, so I'd like to solve this for x. So the first thing I'm going to do, right, with the information that I have here, well, I'm going to go ahead and rewrite it into its equivalent logarithmic statement. So its equivalent logarithmic statement says that log base 3 of 10, right, I would need to raise 3 to the 2x plus first power in order to get 10. So log base 3 of 10 equals 2x plus 1. So by putting it into this logarithmic form, we were able to get this x out of the exponent spot, which is really nice if you want to solve for x. Now, log base 3 of 10, I don't know what that is off the top of my head, but my calculator does, right? So I'm going to go ahead and use natural log of 10 divided by natural log of 3. So now I'm using the change of base formula, and I know that this is 2.0959. 2.0959. I know it goes on. Okay. Again, my goal is to solve for x here. So let's go ahead and subtract 1 from both sides. It's going to be 1.0959 is equal to 2x. And then x is going to be equal to, okay, divide that by 2. I'm going to get my calculator out for this. So again, subtract 1, and then I'm going to divide by 2. So 0.547, we'll say 0.5480. 0.5480. That's what it's approximately equal to. So you can see we can use logarithms to solve for this. But the claim is, right, I've already showed you back in, I think, 1.2, it was a little while ago, how we can use our calculators to verify this answer, right? So if it didn't say use logarithms, we could also graph this to help figure out when these two functions are equal. So let's go ahead and remind ourselves of that really quick. I'm going to go ahead and use the graphing capabilities for my calculator here. And then I'm going to do 3 to the power And in parentheses, this is where I do the 2x plus, get back to graph. I'm sorry, calculator. There we go. 2x plus 1, close parentheses. And then here I'm going to do 10. Enter. And let's go ahead and graph these things. Oh, I graphed something else before and it's way zoomed out. Let's go ahead and do zoom fit. Maybe it'll make it look a little bit better for us. Again, I'm trying to figure out where these two things cross. That's going to be where the x values are equal. That did not help at all. Calculator, you're so sad. Let's just try to do zoom standard, and then I'm probably going to zoom out once, because I think zoom standard usually goes from -10 to 10. There we go. So I'm going to zoom out once. Can I click it? No. Go down. There we go. Zoom out once. Alright, well, I've played enough with this. Let's go ahead and use our calculator to see whether they equal. So I'm going to use second trace to get to calculate. And I want to know where these things intersect. My first curve is that exponential. You can see up there in the top left corner here. You can see this. 3 to the 2x plus 1. Sure. And my second curve, 10. Yes, perfect. Enter. And then a guess. Well, we know it should be somewhere around 0.5-ish. So, I don't know. I did 0.85. I'll hit enter. And it calculates, and it says, the intersection is actually at 0.54795164, which was the exact same thing that we had right here. So you can see you can check this by graphing it in your calculator. Okay. Let's go ahead and move on then. I want to talk about some graphs of some logarithmic functions. What do these things actually look like? You know, if I gave you a graph, what would a logarithm look like? And so I've prepared for us one of these Desmos things again, Desmos graphing calculators. And so I have log base b of x here, and I have a slider for different b values, right? So let's see, you can kind of see, first of all, it has a very interesting domain, right? So you can't plug in 0 into x for your logarithm. It has kind of an asymptote there sort of deal. And it also doesn't take negative numbers. So maybe let's go ahead and remind ourselves back here, before we even get started, that actually all logarithms have a nice domain. And the domain is strictly greater than 0. So it can't even be equal to 0. It needs to be larger than 0. Okay, and so maybe the first type of function that I see looks something like this. So I'm going to go ahead and just sketch logarithm. Looks something like this. I want to know, when do you get sketches that look like this, right? So, for instance, b is positive. It still seems to kind of look like this. And then when you go down, here something interesting happens here. Foomp, right? So that foomp, well, at b equals 1, we have a problem. And remember, this is a base, right? This is an equivalent for a base of an exponential. And for exponentials, we said bases have to be positive, and they have to be not equal to 1. So this kind of makes sense why there wouldn't be a picture here, why this would error out when b equals 1. But you can see when b is less than 1, I'm going to scooch it off just a little bit, it has a different sort of feel to it, right? All of these have a different sort of feel to it than if b is greater than 1. B is greater than 1, it seems to be like an increasing function, all that sort of stuff. In fact, I could zoom this over since we're not even using when x is less than 0. But when b is greater than 1, you can kind of see it's an increasing function, and then when b is less than 1, it's a decreasing function, right? So that seems to be the breakpoint. Let's go ahead. So this is if b is greater than 1, and if b is less than 1, it looks something like this. It still has this asymptote at x equals 0, this vertical asymptote here. Both of them seem to have this, right? We don't want x to be equal to 0. But if b is greater than 0, sorry, if b is greater than 1, it seems to look like this first case. Again, this is my log base b of x. And if b is less than 1, it seems to look like something like this. Okay, so that's what the logarithms look like. And I have just really quick, I want to bring up for us, um, logarithms and exponentials are friends, right? So if you remember something about inverse functions, right? So I'm going to go ahead and graph this kind of equivalent exponential here to some extent. This is b to the x. And you can see that these things are friends. They seem to be symmetric almost. They're very, very similar to one another. Let me zoom in a little bit. So again, I can hit this play button. This is fun. So see, for different b's, they seem to be friends. They seem to be symmetric about some line. And the claim is that line that they're symmetric around is y equals x. If you were to reflect these things across this line, y equals x, you would have the other one. Let's see if I can. Yeah, there you go. All right, so exponentials and logarithms are good friends. Let's go ahead and stop that here. Okay, wrong one. There we go. And finally, the last thing that I want to bring up in our video before our class, I want to do an example here of how can we actually use logarithms to solve a real-world problem. So a radioactive element, which I'm calling element X, decays 1% per year. So 1% per year. Originally, we have 100 grams of element X. So a lot of radioactive elements decay. This is kind of the idea behind carbon dating and stuff like this. We have an unstable, carbon-14 element, stuff like this. So a lot of elements with unstable isotops decay. So this one's special. It decays at 1% per year. I made up an element because I wanted a nice number. And the first thing we want to do then is find a function that models the quantity in grams. I'm going to call this Q, of element X remaining t years from now. So let's go ahead, maybe make a table here. If this is my t and this is my q, right? So my independent variable and my dependent variable. So 0 years from now, the claim is, well, we should have all 100 grams. If I did 1 year from now, well, I wouldn't have my 100 grams, but 1% would decay, so I would have 99% left. So 99% is, of course, the same thing as 0.99. So this is how much is remaining, right? We're not interested necessarily how much decays, but how much is remaining, so there's 99% left. And this is where it gets a little more difficult, right? Because it says it decays 1% per year. So this right here, 0.99 times 100, this is 99 grams, right? And then I need to do 1% of that 99 grams would decay, right? So this is going to be 99 times 0.99, right? So again, 1% of that 99 grams decays. Then another way you can write this is 100 times 0.99, right? So that's what 99 grams is. And then this is times another 0.99. This will become very useful here in just a second. Now let's do one more data point. I'm going to do when t equals 3. This would be 100 times 0.99 times 0.99. So that's what it would be after 2 years. Again, I haven't evaluated this out yet. So that's what it is after 2 years. And then so after a third year, another 1% decays. So I would have 99% left of that. So notice, a way that we could write this is 100 times 0.99 raised to the third power, right? Because 0.99 times 0.99 times 0.99. Likewise, back here, this would be 100 times 0.99 raised to the second power. Right here, this would be the same thing as 100 times 0.99, and if I really wanted to, I could write it as raised to the first power. And even better yet, over here, this could be 100 times 0.99 raised to the 0 power. And hopefully, we're paying attention and we're realizing, oh, there's a pattern here, right? Whatever that t value is, this shows up as the exponent. When t is 1, we have 1. When t is 2, we have 2. When t is 3, we have 3. Again, we're trying to model this situation. We're trying to come up with a function, something that explains what's going on here. And so my claim is, what's going on here is that the quantity of this element x left over is going to be 100 times 0.99 raised to t, the t power. Whatever t is, that seems to be modeling the situation correctly. So this is some exponent equation. And the claim is, in order to answer some questions, we're going to have to use logarithms. Okay, so this is a function that models the quantity remaining. Let's move on to B. Use logarithms to find out how long until there are 50 grams remaining. So I want to know, when is the quantity 50? So quantity 50, and I want to know when, right? How long? So I'm going to be solving for a time. So this is my setup right here. Notice in parentheses I have the words half-life, right? So this is some common terminology that comes up, and we'll talk about it a little bit more in class, right? So this is when there's half of the amount of the original remaining. So instead of 100 grams, it's 50 grams, sort of deal. Okay, so now let's go ahead and try to solve for t. Again, we're going to use logarithms. I know that we could use our calculators, but we're going to practice here using logarithms. So the first thing I want to do is isolate the exponential. In order to do that, I'm going to divide by 100 on both sides. When I divide by 100, this is going to be 1/2 equals 0.99 raised to the t power. Again, my job is to solve for t. T is in this exponent slot, and so I'm thinking, okay, this is a section about logarithms. What if I was to write this in its equivalent logarithmic form, right? So this would be log base 0.99 of 1/2 equals t, right? Again, so that would be the power that I'd have to raise 0.99 to in order to get 1/2. And so the claim is I can plug this into my calculator, right? So let's go ahead and do that. Pull up my calculator and I can figure out exactly what t is. So I guess I don't have log base 0.99, but luckily I have the change of base formula. So I'm going to use the natural log of 1/2, that's the same thing as 0.5, divided by the natural log of 0.99. Enter, and the answer is 68.96 and change years, almost 69 years. So I'm going to say here about 69 years. There's my answer. So that's how long it would take. That's the half-life, I guess, in some terminology. This is how long it would take to go from 100 grams to 50 grams. Okay, a different type of question. Use logarithms to find out how long until there are 10 grams remaining. So instead of 50 grams, what about 10 grams? So the setup is very, very similar. We want to know when is the quantity 10. And so again, the first step is I'm going to isolate the exponential. So I'm going to divide by 100 on both sides. So I'm going to get 1/10 is equal to 0.99 raised to the t power. I'm going to put this into its equivalent logarithmic form. So this is going to be log base 0.99 of 1/10 should be equal to t. So that's the equivalent logarithmic form. And I should be able to go ahead and solve that, log base 0.99 of 1/10, using my calculator. So very similar here. I'm going to pull up the last entry that I had. And instead of 0.5, I'm going to do 0.1. That's the same thing as 1/10. So hit enter. 229 years and change. 229 years and change. Okay, there we are. So that is the final section again here in Chapter 2. Next time we're going to be talking about average rate of change, right? This has been a lot of review of stuff, and we need to get into a little bit of calculus. So that's what Chapter 3 is going to be about, is actually talking about some calculus here. So, all right, I'll see you guys in class, and again, when we make it into Chapter 3.